Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 3, Advanced Factoring Strategies for Quadratic Expressions. So we're starting out with a classwork opening exercise that says, Carlos wants to build a sandbox for his little brother. He is deciding between a square sandbox with side lengths that can be expressed are represented by x plus 3 units and a rectangular sandbox with length 1 unit more than the side of the square and width of 1 unit less. And they gave us a diagram here. So Carlos thinks that the area should be the same because 1 unit is just moved from one side to the other. So he added 1 to the length and subtracted 1 from the width. So he's thinking since he took away the same amount that he added to the other, the area should be the same. So this is a classwork, so I want you to try this. Pause the video, see if you can do these questions, and then unpause the video and come back. Okay, so it says A, do you agree that the two areas should be the same? Why or why not? Okay, well I'm going to skip that for now and come back, and I'm going to show you a quick way to check it after. B, how would you write the expressions that represent the length and width of a rectangular sandbox in terms of the side length of the square? All right, so, okay, so how would I write the expression that represents the length and width of a rectangular sandbox in terms of the side length of the square? In terms of the side length of the square, and this is the side length of the square. So I would say that the length of the rectangle is x plus 3 plus 1, or the length equals the side length of the square plus 1. And the width is x plus 3 minus 1, or the length is s minus 1. Okay, so I want to point out a common mistake here. Since we have these parentheses here, we don't know what x is, and we don't want to add 1 and say that's x plus 4 and this is x plus 2. So leave it in terms of the square, which is, we have to have that x plus 3 in the equation. Okay, part C. If you use the expressions for length and width represented in terms of the side lengths of the square, can you then write the area of the rectangle in the same terms? Okay, so now that we have these, now I always ask my students to write a formula. Area equals length times width. Try that again. Length times width. So area equals the length x plus 3 plus 1 times the width, which is x plus 3 minus 1. That's a little messy. Let me redo that. Okay, so there's the equation for area. Area equals length times width. So there's my length and there's my width. Okay, so part D says, how can this expression be seen as the product of a sum and difference a plus b, a minus b? So I copied over my answer from C just so we're not flipping back and forth. And if you notice x plus 3, that's my first term, and my first terms here are the same. So I will let A equal x plus 3. And I will let B equal 1. See how 1 is the same as over here and here? And there's a plus and a minus. So I'm going to let B equal 1. And so here's my B's and here's my D's. They're the same. Okay, so let A equal x plus 3 and let B equal 1. And now I can rewrite this as A plus B, A minus B let's see. Okay, so E, I guess that's all they wanted here. Let A equal x plus 3 and B is 1. Can you now rewrite the area expression for the rectangle as the difference of squares? Okay, so if A plus B times A minus B, which is what we have, A plus B times A minus B, can I rewrite it as A squared minus B squared? Okay, so since we have that setup, A plus B times A minus B, so I'm just going to write these here again. Here's A, here's B, and there's a plus sign. Here's A, here's B, and there's a minus sign. So here's A plus B, A minus B, and we're multiplying. And so hopefully that makes it clearer. So since A plus B times A minus B is A squared minus B squared, I know that A is x plus 3, so now I'm going to just substitute in my A for this A squared. I'm going to say, okay, well, A is x plus 3, so therefore I'm going to square it, and minus B squared. Well, B is 1, minus 1 squared. Okay. So since 1 squared is just 1, my answer would be x plus 3 squared minus 1. F. Look carefully at your answer to the last question. What does it tell you about the areas of the two shapes? Okay, so now if I go back, the area of the square is x plus 3 squared, x plus 3 times x plus 3. But the area of the rectangle is not x plus 3 squared. So what I'm saying here is, since the sides of the square were x plus 3 and x plus 3, the area of the square was x plus 3 squared. Okay, the area of the rectangle is this, which is x plus 3 squared minus 1. All right? So it tells us that the area of the rectangle is 1 unit less than the area of the square. So they are not equal just by adding 1 to one side and subtracting 1 from the other. So then it says, can you verify that our algebra is correct using a diagram or visual display? Okay, so this is going to be hard to draw, but I'm going to do the best. All right, so if I draw a rectangle or a square, just trying to make this as neat as possible. Okay, it's recognizing a squiggle. All right, bear with me here. There we go. Got to draw faster, I guess. Okay, so this is x. All right. Let's go back to my other pen. This is x by x. Okay, but then I need a plus 3. So what I'm really doing here is algebra tiles. So if this is 1, this is 2, and this is 3, there's my x plus 3. But I need to do the same down here. So here's 1, here's 2, here's 3. So here's x plus 3 by x plus 3. Well, this is going to continue out here, if you've ever used algebra tiles. And that will give us our answer. X squared plus 6x plus 9. This would end up being x squared plus 6x plus 9. Okay, this is x by x, or x squared. Here's an x, here's an x, here's an x. That's 3, 4, 5, 6, and then 9 little squares, which are your constants. Now if I do the same over here and just add 1 to one side, so I have my x by x, that's still there, but then I'm going to add 1 over here. So that's x plus 4. And I'm going to subtract 1 over here. So instead of 3, I'm only going to do 2. So here's x plus 2. So I added 1 to one side and subtracted 1 from the other, which is what they did right here. added 1, subtracted 1. Okay? And that is going to create this diagram. So this is my x squared, and I have 1, 2, 3, 4, 5, 6 x's, so that's plus 6x. So far so good, but we have a problem here. 1, 2, let me change colors. We have 1, 2, 3, 4, 5, 6, 7, 8. So if you notice, that is the same polynomial except for the constant is 1 less. And there it is. X plus 3 squared, x plus 3 squared minus 1, which is here. Okay, now let's go back to A. Do you agree that the two areas should be the same? Well, you can always substitute a number in and check to see if it's true. So let's let x equal, I don't know, 5. And in this case, it would be 5 plus 3 by 5 plus 3. Okay, does everybody see what I'm doing here? I'm multiplying length times width. So this would be 8 times 8, which is 64. Okay, and then if I say, well, if I plug in a 5 on over here, then I'm going to get x, no I'm not, I'm going to get 5 plus 3 plus 1 times 5, substituting in for my x, plus 3 minus 1. Well, we're working left to right since it's addition. So 5 plus 3 is 8 plus 1 is 9 times 5 plus 3 is 8 minus 1 is 7. 9 times 7 is 63. And as you can see, this one is 1 unit less than this one. So we could have just plugged in a value and checked. Okay. Okay, example 1 here says in lesson 2 we saw that factoring is the reverse process of multiplication. We factor a polynomial by reversing the distribution process. Consider the following example of multiplication. So they're taking the quantity x plus 3 times the quantity x plus 5, and they're foiling it, taking the first term times the first term, which is x times x, x squared. Outer is x times 5, which is 5x. Inner is 3 times x, which is 3x, and 3 times 5 is 15, the last. And then we combine our middle terms, 5 plus x plus 3x is 8x, and then our final polynomial is x squared plus 8x plus 15. When we compare the numbers in the factored form with the numbers in the expanded form, we see that 15 is the product of the two numbers 3 times 5, and 8 is their sums, 3 plus 5. The latter is even more obvious when we look at the expanded form, which is right here, because we see it. They're adding the 5 and the 3, and then this is the product of 5 and 3. It says, can you explain why the relationship exists between the numbers in the factors and the numbers in the final expanded form? Okay, so here's the explanation. The coefficient of the term with a variable to the first degree, that's our linear term, the coefficient, which is this, the coefficient of the term with the variable to the first degree, the linear term, in this case 8, is the sum of the twos. They're talking about this here being the sum of 5 and 3. The sum of 3 and 5. The constant term in the quadratic, which is 15, is the product of the two constant terms, 3 times 5. So make sure you observe this connection rather than just memorizing the procedure. Example 2. Now compare the expansion of the binomial product to the one above. So we have 2x times the 1x is 2x squared. Okay, in this case, we have a 3 and a 5. But we have to look at this. Okay, so this one's a little bit different. So it says, in the expression lying between the two arrows, this one here in the middle, Before like terms are combined, we can see the coefficients of the split linear terms of positive 10x and positive 3x. So these two right here. Also notice that for this example, we have coefficients on both x terms in the factors, and that one of the coefficients is not 1. Okay, so one of the coefficients here is not 1, it's 2. We have 2 and 1 as the factors of the leading coefficient in the expanded form, and 3 and 5 as the factors of the constant term. Get ready for quadratic expressions in factored form where neither of the x term coefficients are 1. Okay, now it says, how is this product different from the first example? Okay, well, it's different because we can't just say, well, 3 times 5 is 15, there's the 15, that's okay. But if we just added that 3 and 5, we'd only have an 8 here. So we have to multiply this 2 times 5 and get 10. Okay, and that's the difference. So let me bring in the official explanation. Okay, so the coefficient of the term with a variable up to the first degree, the linear term in this case, is 8. Wrong one, just a moment. Okay, this one's better. When comparing the factored forms, we see that they are the same except for the coefficient of the first factor in example 2, i.e., for example 2. It is important to point out that the other factors has an x term with a coefficient of 1. There will be examples in the future where both terms have coefficients that are not 1. When comparing the expanded forms of both examples, the green numbers, the quadratic terms, 2x squared, and one of the linear terms, 10x. Okay, so what they're talking about here is the quadratic term and one of the linear terms are different in the example because of the new leading coefficient 2. The other two terms in the expanded form, the 3x and the 15, were not affected by the leading coefficient. Okay, the 3x here and the 15 were not affected. So there's a 3, there's a 3x, there's a 5 times 3, and there's the 15. Okay, a visual on this would look like so. Okay, so if you go back to making a table, this is what it would look like, and you see that you get 2x squared for your first term. You have to add these two terms because 5 times 2x is 10x. So we aren't just adding 5x and 3x. We have to multiply by 2 to get this piece here. So the only change that occurred is in the linear form was this. That's what they're saying. B says, why are the split linear terms different in the two examples? Okay, so in the first example, the linear coefficients are 5 and 3. For the second example, they are 10 and 3. Most students will notice that both products have a 3x, but one has a 5x and the other has a 10x. So that's what I was saying. The only change was that one linear term, or the 2 times 5x for the other linear term. The difference is because the leading coefficient, which doubled 2 of the 4 terms of the expanded expression between the arrows. So this 2 doubled this, and it doubled this. Okay, this next page here explains their way of doing this, but I have a different way that I prefer. If your teacher does it this way, that's fine, but I prefer this. It says that now that we have 4 different numbers, coefficients in each form of the expression, how can we use the numbers in the expanded form of the quadratic expression on the right to find the numbers in the factors on the left? So what they're talking about is, if we have this here, how do we find these factors over here? So in other words, how do we find the factors of this? That's what they're trying to explain. And there's different outcomes that we could possibly have. But the way I do it in my class is I tell students to list A, B, and C. A is 1, it's right here. B is 8, and C is 15. Okay, so then I say factors of C that add up to B. so there's my rule. I made it a little bit more legible. Factors of C that add up to B. Factors of C that add up to B. Factors of C that add up to B. Since C is 15, then I do a factor table here, and I say, well, factors of 15 are 1, 15, 3, 5. And they have to add up to 8. So the sum has to equal 8. Well, there it is. So it would be x plus 3, x plus 5. Okay, but now when we do the other one, this one, that where we have a leading coefficient other than 1, we can't do factors of C that add up to B because there are no factors of 15 that add up to 13. It just doesn't work. So I'm going to change my rule a little bit here, and it's going to be factors of A times C. Okay, let me just put a dot there. So it's factors of A times C that add up to B. So factors of A times C that add up to B. So I'm looking for factors of 30 that add up to 13. So I have 1 times 30, 2 times 15, 3 times 10, and there it is. 3 plus 10 is 13. 3 times 10 is factors of A times C. So I know it's 3 and 10. So how I do this is I multiply the 2 over by the 15. I call this the Beats method because back in the day I used to use red ink, and headphones look the Beats headphones. So these look like earphones. So I take the 2 times the 15, the left ear times the right ear, and get rid of that first term. And that's the first thing I did. And then I take factors of C that add up to B, so my old rule. And that will give me x plus 3, x plus 10. Okay? All right, but x times x is not x squared, it's 2x squared. So I multiplied by 2, so now I have to divide that back out, like so. And if I have a fraction that is not a perfect, or it can't be divided, then the denominator goes out in front. So that's going to become 2x plus 3. This one can reduce x plus 5. And voila, we have 2x plus 3 times x plus 5. Okay? This is the way I'm going to be doing it in my videos from now on. If you prefer to do the way they explain down below here, which I'm not going to go over, that's up to you. But I prefer this method. I call it the Beats method. Old school, I guess. No, students, I think, still wear Beats. Are they Bluetooth now? All right, anyway. Example 3. Now try factoring the quadratic expression with some negative coefficients. Now we have 3x squared minus x minus 4. So remember what I did. I do my Beats. So I go like that. 3 times negative 4, and I'm going to rewrite this as x squared minus x minus 12. Factors of 12. 1 times 12. 2 times 6. 3 times 4. Those are all the factors of 12. But it has to be a negative 12. So one of these has to be negative. Well, my middle term is negative, so the bigger number when adding to get a negative, the larger absolute value has to be the negative one. So when I add these up, I'm looking for negative 1. There it is. So I'm going to rewrite this as x plus 3, x minus 4. Don't forget, we multiplied by this 3, so I have to divide that back out. This reduces to x plus 1. This doesn't reduce, so that becomes my coefficient of my linear term. So the answer is x plus 1 times 3x minus 4. And as you can see, the beats method works. Okay, so exercises. So now try these. You might want to go back and read the steps that you did in class or the last page examples, or you could use my beats method, whatever you're more comfortable with. And if your teacher accepts the beats method, use it if you like it. For exercises 1 through 6, factor the expanded form of these quadratic expressions. Pay particular attention to the negative and positive signs. Okay, so remember, I'm doing the beats method. I'm going to take my 3 times my negative 8 and rewrite this as x squared minus 2x minus 24. Factors of negative 24. I keep trying to write a 4 and it looks like a 9. Factors of negative 24 are negative. Oh, my middle term is negative, so it's going to be small, positive on the smaller side. So get rid of that negative sign. So let's do 1 times negative 24. Do you understand what I'm saying here? There's not my 4 again, looking like a 9. When this is negative, your sum, your bigger number has to be negative in your sum. All right, so 2, negative 12. 3 times negative 8. 4 times negative 6. And that's it. I'm looking for a difference of 2, negative 2. There are my sums that would be negative 2. So I rewrite this as x plus 4, x minus 6. We're not done. Do not forget this 3 here. Don't forget to divide by 3. Divide by 3. If I can't divide, it goes out in front. 3x plus 4. There's that 9 again, looking like a 4. And this reduces. X minus 6 divided by 3 is 2. So there is this factor. Okay? Okay, number 2. Beats method. Take the 3 times the negative 8. I'm looking for factors of negative 24 again. The middle term this time is positive, which means the bigger number is going to be positive, so this is going to be negative. Negative 1 times a positive 24, when I add them, will give me a positive sum. Negative 2 times 12. Negative 3 times 8. Negative 4 times 6. That is a 4. All right, so I'm looking for 10. Well, it's right here. So I'm going to do this over here. So that's going to be x minus 2 times x plus 12. Don't forget your 3 over here. Now we're going to divide that back out and we're done. That will not divide, so that goes out in front. 3x minus 2 and x plus 12 divided by 3. And there is my answer. 3x plus 2, x plus 4. Okay, number 3. Are you getting a hang of this beats method? Let's try it again. Leading coefficient 3. I covered it so we can't read it. Leading coefficient of 3. Constant of 14. Negative. So I'm looking for factors of negative. 3 times 4 is 12. Carry the 1. 3 times 1 is 3 plus 1 is 4. I'm looking for factors of negative 42. The middle term is positive, so my bigger number is positive, my smaller number is negative. Negative 1 times 42 is negative 42. Negative 2 times 21. 3 times 14. 4 won't go, 5 won't go. Negative 6 times 7. We want a difference of 1. My b is 1. Oh, and I've been bad. I have not been doing this. A equals 3. B equals 1. C equals negative 14. Factors of A times C that add up to B. Okay. So now I have this. Now I'm going to write x minus 6 times x plus 7. I've multiplied by 3, so I have to divide that by 3, and I have to divide that by 3. If it is divisible, then I divide it. If it is not, the denominator becomes my coefficient. And my answer is x minus 2, 3x plus 7. Okay. Number 4. A equals 2. B equals negative 21. C equals negative 36. I'm looking for factors of A times C, so I'm looking for factors of negative 72. 36 times 2. And I have a negative 21. That's negative, so my smaller number is going to be positive. A bigger number is going to be negative. So it's 1 times negative 72. That's a sum of negative 71. I'm looking for the sum of negative 21. Keep going. 2 times negative 36 would give me a sum of negative 34. And that's not 21. 3 times negative 24. There's my difference. There's my sum of negative 21. So it's going to be x plus 3 times x minus 24. All right, I factored out this a, so I have to, or I multiplied by a, so I have to get rid of it. 3 will not divide by 2. 2x plus 3. And 24 is divisible by 2. And there's my answer. So notice what it says here. This might be a challenge. If it takes too long, try the next one. It didn't take any more time than the others if you use my beats method. This was just as easy as any other one, and the answer came just as quickly. There was no challenge. It is just a routine. All right, are you liking the beats method? I hope so. Okay, A equals negative 2. B equals 3. C equals 9. Factors of A times C. Negative 2 times 9 is negative 18. I'm looking for factors of negative 18. My middle term is positive, so my bigger number is going to be positive. Negative 1 times 18. That's a sum of 17. That is not 3. Negative 2 times 9 is negative 18. 9 minus 2 is 7. That is not 3. Negative 3 times 6 is negative 18. 6 minus 3 is 3. Ding, ding, ding. X minus 3. X plus 6. Put my a back. Divide by negative 2. Divide by negative 2. These don't divide. Move that out in front. Okay. I made a mistake. The negative leading coefficient threw me off. Okay, so I made a little mistake here, but it's not difficult to fix. So be aware that in math, you don't always get the right answer the first time. You realize your errors and you fix them. So I'm going to fix this. So what we need to do here, if you're going to use the beats method, is factor out a negative. So I'm going to rewrite this as negative 1 times 2x squared minus 3x minus 9. Okay, and then I'm going to work with this middle inside here. So now a is positive 2, and b is negative 3, and c is negative 9. So I'm still going to do factors of 2 times negative 9, which is negative 18. I should not have erased this. But now I want my negative to be in here. So this bigger number's got to be negative. 1 times negative 18 is a sum of negative 17. 2 times negative 9 is a sum of negative 7. 3 times negative 6 is a sum of negative 3. So I'm going to rewrite this as negative 1 times x plus 3, x minus 6. Whoa, what just happened there? I did not use the eraser. Why is this erasing? Okay. Negative 1 times x plus 3 times x minus 6. Remember that we factored out a 2, so I'm going to divide by 2. Divide by 2. This is the same as the beats method, just don't forget this negative 1. So it's negative 1 times, this goes over here, 2x plus 3, x minus 3. Okay, now we don't know where the negative 1 goes. Does it go to this or does it go to this? Okay, now we have to look at our last term. Our original was positive 9, and my original middle term was a positive 3. If I multiply this by negative 1, I get negative 2x minus 3, and a negative times a negative is positive. But then I have a negative 2x times x, which is a negative 2x squared. I have a negative 6x and a negative 3x, which is negative 9x. Okay, so I do not want this to be negative because then I'll get 3x in the middle. Okay, let me explain that. I'll do both. So if I multiplied this by negative 1, I'd get negative 2x minus 3. And this would be left with x minus 3. When I FOIL that, I get negative 2x squared plus 6x minus 3x plus 9. And when I combine these two terms, I get negative 2x plus 3x plus 9, which is my original. And if I do it the other way, if I multiply this by negative 1, then I will get 2x plus 3 will stay positive right here, but I'm going to multiply this negative 1 times x, which is negative x, and multiply this negative 1, and it's going to be plus 3. So 2x times negative x is negative 2x squared. 2x times 3 is 6x. 3 times negative x is negative 3x. And 3 times 3 is 9. And when I combine like terms, I get negative 2x squared. 6x minus 3x is 3x plus 9. So these come out to look like they're the same. Okay, so is this correct or is this correct? Okay, so I decided to double check this because I am intrigued when things like this happens. And I put in a graphing calculator, my original term here. I put in my factored form from Beats method here, and I put in my factored form with the negative 1 going to the other parentheses here, and all three of these graph identical. So there are two solutions to this answer, to this problem. This is correct, and this is correct. Okay, now we have one with fractions. There's a couple of ways we can do this. I'm going to show you one way right here. I'm going to take this whole thing and get rid of that fraction by multiplying by 16. So that's going to distribute here and give me 16r squared plus, well, this 4 will reduce this 16 to 4, and 4 times 6 is 24r. And these 16s would cancel, leaving me with 9. Okay. And then I always check for a greatest common factor once that's done. 9 only has multiples of 9, 1, and 3. 9 won't go into 24. 3 will, but 3 won't go into 16. So this is not, there's no GCF here. So my A is 16. My B is 24. And my C is 9. Okay, so factors of A times C. 16 times 9 is 160 minus 16, 144. So I'm looking for factors of 144 that add up to 24. Well, it should jump right at you automatically, but I'm going to do this anyway. It's 1 times 144. Or it could be 2 times 72. Or it could be 3 times 48. Or it could be 4 times 3 is 12, 24, 6. 5 won't go. 6 times 2 is 12, 24 is 4. 7 won't go. 8. Let's see, 8 times 2 is 16. 8 times 1 is 8. 60, yes, 8 will work. 8 goes into 14 once. There's a remainder of 6. 8 goes into 64 8 times. So there's 818. Remember, I'm looking for a sum of 24. So we have 145, 74, 51, 40, 30, 26. We're getting closer. And if you're really good at multiplication, this is what knowing your foundation skills comes in handy. So now 9 won't work. 10 times 14.4, we don't want that. 11 won't work. And 12 times 12 is 144. That is a sum of 24. Beautiful. So we have r plus 12. R plus 12. We divided by 16. Or multiplied by 16, so we need to divide by 16. Reduce. So r plus 3/4 and r plus 3/4. There's that 4 looking like a 9. Okay. Move the 4 out in front of the r because it will not divide the 3, or 3 won't divide by 4. 4r plus 3 times 4r plus 3. Okay, it doesn't reduce. I could leave it like this. I could put it like this, or I can leave it like this. But that is r plus 3/4 squared. Okay, so my beats method even works with fractions if you get rid of the fraction. All right. Okay, so continuing, always look for a GCF first. 100 factors are 10 times 10, 100 times 1, 25 times 2, and so on. 20 are factors of 2 times 10, 4 times 5. But 63 is 9 times 7, and no factors of 5, no factors of 2 because it's odd, and so on. So there are no greatest common factors here. So if I continue with my beats method, this is going to be a pretty big number. A is going to equal 100, B is going to equal -20, and C is going to equal -63. So factors of A times C would be -6,003, or 6,300, or 6,300. And I want those factors to add up to 20 on the negative side. Okay, so that's a really big number. So if you have a calculator, that would work. So it would be, and since my B is negative, I want this side to be negative. So it's 1 times -6,300. 2 times negative and half of 6,300 is 3,150. And 3 times -2,100. And 4, let's see. Okay, so I did this behind the scenes, even though my beats method, factors of A times C that add up to B, work every time. Sometimes it's a lot of work with really large numbers. 100 and -63 resulted in a really large product. And I did this with the calculator behind the scenes, and I finally got down to the difference of -20 right there, 70 and -90. So it took me quite a while, and I'll show you another way if our numbers are too large to deal with. So it's x plus 70, x minus 90, and I divided by 100, divided by 100. So these reduce to 7/10, these reduce to -9/10, and then after reducing, I move the number out in front, so it will be 10x plus 7 and 10x minus 9. Okay. Another way you can do that is if you see that this is there's a 10 in here and there's a 10 in here, you can do it like so. 100x squared would be 10x squared. If you distributed 100x squared minus, and then factor out the 2 times 10x minus 63. Okay? So I factored out a 10x from both, is basically what I did there. And then once you do that, just factor it. You have a 10x here, you have a 10x there, so that's your first term. Okay, and then you just have to look for factors of 63. And it's not in the difference of negative 2, so it's minus 9 plus 7. And you get the same answer. So yes, this way is a lot easier than this way when you have very large A's and C's. Okay, so keeping with this form now, I notice I have a y squared here and a y squared in here, so I can factor that. So I can call the first term y squared squared. Remember your power rule. Exponent to another power, you multiply, and then you say plus 2 times y squared minus 3. And that will give us y squared as our first term. And I am looking for factors of 3 that add up to 2. So it's going to be positive, so it's going to be plus 3 minus 1. This is a difference of perfect squares here, so we're not done. Always check that. Y squared plus 3. And this is a difference of squares where A is y and B is 1. So it's plus 1 minus 1, because 1 times 1 is 1, and positive 1 times a negative 1 is negative 1. So my final answer is y squared plus 3 times y plus 1 times y plus 1, or minus 1. Okay, number 9. This has a GCF. 9, 3, 12. I'm going to factor out a 3, leaving 3x squared minus x minus 4. And once I do that, I'm going to use my beats method. So my A is now 3. My B is negative 1. And my C is negative 4. And I want factors of A times C, which are negative 12. I want factors of negative 12 that add up to negative 1. So my bigger number is going to be negative. So 1 times negative 12, if you add that, that's negative 11. 2 times negative 6 adds up to negative 4. 3 times negative 4 adds up to negative 1. So there is the numbers I want. So don't forget this 3 out here. And then I have x plus 3, x minus 4. And then don't forget to divide by our A. So then I get 3 times x plus 1 times, and then move this out in front, 3x minus 4. And there's my factored form. Okay. Number 10. Even, even, even. 2 will go into all of these, 4 will go into that, 4 will go into that, but 4 will not go into that, 6 will go into that, but not those, so I can factor out a 2, leaving 8a squared b to the 4th plus 20a b squared, not 20, forgot to divide, 10a b squared minus 3. Okay, just change the color there. Okay, so now what we want to do is, looking at this, we have an A, we have a B, we have an A, we have a B, but this is a power of 2, this is a power of 4, this is a power of 1, this is a power of 2. I could factor out an A from, so there's different things we can do here. But now when I look back up here, if I don't do this rule here, if I only focus on this portion, And ignore that 6 for a minute. Watch what we can do. Let me erase this. And I'm going to, I see that there is a 4 in 20 and 16. So I'm going to factor out a 4. There's an a, and there's b squared in both terms. So I can factor those out. And if I square that, 4 squared is 16, a squared is a squared, b squared to the squared is b to the 4th, plus, now if I have 4ab squared again, then I put the parentheses in the wrong place, 4ab squared again. Okay, what did I have to factor out to get that? A 5. And then we have our minus 6 over here. Okay, so we have 4ab squared a b squared as my first term, and then I need factors of -6 that add up to 5. So 3 times 2 is 6, and 3 plus 2 is 5, so it's going to be minus, let's see, could be -3, -2, but that doesn't add up, so it's going to be -1 and plus 6. 6 times -1 is -6, 6 minus 1 is 5. Okay, so there it is, and now I can factor out that 2 I did before. So if I factor out a 2 now of this piece, then I'd have 2 times 2ab squared plus 3 times 4ab squared minus 1. Okay. That is the end of Lesson 3. Review the lesson summary and go to your problem set.